Okay, right. Let's move on to a new chapter. Okay, so this chapter should be relatively straightforward. Okay, now let's do thermal properties of materials. Okay, your current chapter is really about study about heat energy and how it affects heating. All right. Okay, now to start it off, we need to go with what is kinetic model of matter. So kinetic model of matter tells you that matter is composed of many small particles that are in constant random motion. When we're talking about matter, we know that there are three states of matter, right? Where we say that you have solid, you have liquid, and you have gas. Okay, so states of matter can be classified as either one of these three. Okay, so we say that matter is composed of many small particles that are in constant motion. So these small particles that we're referring to are called atoms or molecules. And then what determines the states of matter is dependent on how these particles are arranged in the first place. Okay, so what you're seeing over here in the screen, the description is probably something that you would have learned from IGCSE or SPM before. So when it comes to solids, we know that all the molecules are generally packed close to each other and held in place by strong intermolecular bonds. Okay, the bonds are actually preventing your molecules from moving, giving your solid their rigid shape. Okay, your molecules in a solid generally are arranged in a regular pattern and they only vibrate about fixed positions. Okay, so this is for solid. The main thing is that those particles do not move. I mean, they don't move about freely. They only vibrate about the fixed positions, and they seem to be arranged in a regular pattern. Okay. Now, when we move on to liquids, molecules are still close to one another, but they are no longer arranged in a regular pattern. Okay. There are no patterns to see for the molecules inside liquid. Okay, so the molecules actually have enough energy to break the intermolecular bonds between them such that they are now able to slide past each other. So for a liquid, the molecules can actually move about as they slide past each other. This is what allows a liquid to flow in the first place. Okay, so this is for liquid. And then the last thing would be for gas. For gas, the molecules are very widely separated, generally 10 times further apart than in liquids. They also move about freely and randomly at high speeds, and they have no intermolecular bonds between them. Okay. Solids would have intermolecular bond that is confirmed. Liquids would have very weak intermolecular bonds and it can be easily broken. For gases, they have no intermolecular bonds at all. All right. So it's because of this they can actually move freely and randomly. All right. And because your molecules have wide separation, that means you have large spaces between the molecules. So the large spaces between the molecules would mean that your gases can be easily compressed and expanded as you like. Okay. So what you see below here is a visual representation of how the solid, liquid, and gas molecules ought to look like. All right. So for solids, in general, tightly packed, regular arrangement, vibrate only about the fixed points, and are strongly bound together. For liquids, still tightly packed, but not as tight as solids. There are no regular arrangement between them. The molecules can slide past each other, and they are not fixed at any point because they don't have any bonds between them. All right. And then lastly, for gases, they are widely spaced, they move freely and randomly at high speeds, and there are no bonds whatsoever between the molecules. Okay. Right. So this is something like a revisit of what you learned in SPM or IGCSE. Okay. They do ask you about this in your exam questions, but it's very, very, very rare. The only time they've ever asked you about this was, I believe, in June 2020, I think. Yes. The only time they've asked you about the arrangement of molecules in one of the states of matter was in June 2020. Okay, so that was the only time that us, wait, I think this is not June 2020, this one is June 2021, my mistake. Okay, in June 2021. The only time they've ever asked you about this is actually in June 2021. Okay, the rest of the years they never really did ask, but it is still inside the syllabus, and they have actually asked it once before. Okay, the more common thing they ask is what comes after this is page 2 onwards. All right, so now just now we went through how the molecules or particles behave, how the molecules or atoms behave in solid, liquids, and gases, right? So let's look at the molecular kinetic energy of these molecules. All right, so when molecules move or vibrate, they tend to have kinetic energy because of the motion. In solids, they will vibrate. In liquid or gases, they will move. So they have motion, they have kinetic energy. In general, when temperature increases, these molecules tend to move faster, hence their kinetic energy increases. Okay, we can say that molecular kinetic energy is directly proportional to temperature in Kelvin. This one you will see in a chapter called ideal gas later. We will revisit this statement again in a chapter called ideal gas. All right, but for now, just think of it as this: when you're talking about the kinetic energy of molecules, it is actually affected by its temperature in Kelvin. The higher your temperature, the higher your kinetic energy. The faster the molecules will move, the faster the molecules will vibrate. All right. So when you're talking about the kinetic energy of the molecules, they they all tend to move at different speeds. Hence, there will be varying or random kinetic energies. Okay. So this one is talking about the kinetic energy of the molecules. All right. I'm not talking about the kinetic energy of the body itself. What I mean by that is this. Let's just say I have a solid here like this. And then I tell you that the solid is made out of particles or atoms like this. Your particles will only vibrate about their own mean position in this manner here like this, right? So when we're talking about the molecular kinetic energy, we're talking about the kinetic energy of these molecules itself when they are vibrating. Okay, we're not talking about the kinetic energy of the whole solid. I mean, you see, I could have this solid here, which is stationary. The kinetic energy of your solid is 0. But if you were to single out the atoms or molecules that make up the solid, the atoms or molecules are not stationary. They are actually vibrating. They are actually moving. So they have kinetic energy. So when we're talking about the molecular kinetic energy, we are talking about the molecules or atoms themselves. We're not talking about the entire object as a whole. We're talking about the molecules inside that object. Okay. So just to make things clear, right? So when we're talking about the kinetic energy and potential energy here, we're talking about the molecular ones, not that of the whole object. Okay, so you don't get confused now. All right. Okay, now back to the notes. Just as we have molecular kinetic energy, we also have molecular potential energy. All right. Molecules in general tend to have intermolecular forces between them because of the attraction of negatively charged portion of one molecule with the positively charged portion of another molecule. So what do we mean by that is this. Let's just consider a hydrogen chloride molecule, HCl. If you learn chemistry, you would know hydrogen chloride is a very common molecule, right? It's something that you see often. So let's just say that you're talking about hydrogen chloride molecule. You have 2 of them right now, okay, and they somehow are situated very close to each other, like this one here, like the ones that you're seeing right over here. Okay, sorry. Let me just go out. Okay, right. So you have your hydrogen chloride molecules like this. Now, For these hydrogen chloride molecules, there will be some portions of it that is slightly positively charged, and there'll be another portion of it that is slightly negatively charged. Okay, if you take chemistry, you understand that there's a certain concept called polarity. Okay, for that particular molecule or atom, there's certain portions that are positive, certain portions that are negative. So here, if you look at the hydrogen chloride molecule, the hydrogen is positive, the chloride is negative. Okay, so this is what we're seeing right now for the molecules. So the thing here is that if your hydrogen chloride molecules come close to another hydrogen chloride molecules, your negative here would be attracted to the positive here. Likewise, the other positive here will be attracted to the negative here. So this is what we mean by your intermolecular forces. And this is what we mean by your intermolecular forces. Okay, so your case here is that because your molecules have forces of attraction with each other, intermolecular forces with each other, if you somehow want to increase the separation between the molecules, let's just say that there's a separation between the molecules like this is distance d. If you want to increase the separation, you actually have to overcome the attractive forces. So work must be done to overcome these attractive forces. So you learned that under AS physics last time, when you do work, it usually is used to increase the energy of something, right? So in your case, it's actually increasing the potential energy of the molecules. Okay, it's increasing the potential energy of the molecules. Hence the word molecular potential energy here. All right. So in general, if you increase the separation, you have to do more work. So your molecular potential energy obviously will increase. All right. And then if let's say your separation decrease, your molecular potential energy will decrease. All right. It's written here as vice versa. It means that when separation decrease, molecular potential energy decrease. Okay. And then there's also another thing that will affect your molecular potential energy. That one is your bonds. Okay. What we'll tell you is that if you break the bonds between molecules, your molecular potential energy will increase. Okay. And vice versa. Meaning to say, if bonds are formed, molecular potential energy decrease. This one, it will make more sense if you look at the next page later on. Okay. The first one here, this one I think is easily understood why potential energy will increase when separation increase, because you simply have to do more work to increase the separation. But for the second part, where we tell you when bonds are broken, molecular potential energy increase, this one you have to refer to the next page example. Okay. Now, because your molecules are always at different distances from each other, same thing as before, your molecular potential energy, the value will keep on varying, or you have random values to your potential energies. Okay, so now that you know that for your molecules or atoms that constitute matter, there is molecular Ke and molecular potential energy. If you were to sum up these molecular kinetic energy and potential energies, if you to sum up the random values of all these molecular potential and kinetic energies, you will have a quantity called internal energy. Okay, this is the main thing in your current chapter, internal energy. All right, internal energy is actually defined as this. It is the sum of a random distribution of kinetic and potential energies of molecules in the system. Okay, if you take a particular system, it can be a solid, it can be a liquid, it can be a gas. Doesn't matter whether it's a solid, liquid, or gas. The molecules inside all have kinetic energy because of their motion, and they all have potential energy because of the attraction between the molecules. And the values of these energies are all random. Okay, because for Ke, the molecules always move at different speeds. For Pe, the distances are always at different values. So the values are random in the first place. If you sum up the random values of all these Ke and Pe of your molecules, you're getting a quantity called internal energy. Okay, so this one is a definition that always comes up for this chapter. They will always ask you to define what is internal energy. You need to use this definition. Okay, all right. So worded in an equation, it just means this not internal energy, i.e. is kinetic energy Ke plus potential energy Pe. Okay, now from here you can actually do some things to this equation. If internal energy is kinetic energy plus potential energy, this would mean that change in internal energy is the sum of changes in Ke and potential energy of molecules in the system. In other words, IE equals to Ke plus Pe. Change in IE is equals to change in Ke plus change in Pe. Okay, that's what it means. All right, you're just changing it to change in quantity form. Okay, now from here, you need to be careful a bit once you deal with ideal gases. If you're taking chemistry, you already probably learned about ideal gases already. Okay, physics A2 also has a chapter called ideal gas, but I haven't gone through it with you yet. Now, one of the things about ideal gas is that ideal gas has no intermolecular forces. Okay, so because intermolecular forces is not present for an ideal gas, it means that there are no molecular potential energies. Just now I mentioned to you that your molecular potential energy comes about because there are forces of attraction between your molecules, right? So if you already know that an ideal gas by definition doesn't have intermolecular forces, this means that you will have no molecular potential energy. So if just now I told you that internal energy is Ke plus Pe of the molecules, because your Pe is no longer present, your internal energy is just going to be your kinetic energy for an ideal gas. Okay, and then from here you can also just modify it a little. If internal energy is kinetic energy of the molecules, change in internal energy is equals to the change in kinetic energy of the molecules. Okay, so that's one. And also another thing that you can do from here is this. Since kinetic energy of molecules is directly proportional to thermodynamic temperature, internal energy of an ideal gas is proportional to thermodynamic temperature. Okay, it's because of this. This one actually came from the top portion here, where we tell you that kinetic energy is directly proportional to temperature in Kelvin. So here, if you look at this one, just now it was mentioned that IE is equal to Ke. This is for ideal gas. Okay, and then we also know that Ke is proportional to temperature. So if I go and sub it inside here, related with the first equation, this would mean that internal energy is proportional to temperature, which is this one. Okay, internal energy of ideal gas is directly proportional to its temperature. Okay, you will see this kind of relations a lot later on in your past year. Okay, so just know what the equations mean and how do they relate to each other for now. Okay, now let's go to the next page. All right, next page. Now, what happens when you try to heat a particular substance from solid all the way to gas? Okay, this is your graph that looks like this. Okay. Now, during the process in which you are heating out your substance from here to here, we generally say that heat is supplied, internal energy increases. Okay, so going from this point all the way to this point, you are continuously heating your substance. Heat is supplied we also say that internal energy is increasing here. Okay, so there are a few things that you should be able to analyze from the substance as you continue to heat it out through the different phases of matter. Now let's just look at for state 1. Okay, when it was a solid. Now whatever heat you supply causes the temperature of the solid to increase until its melting point. At this point here, we will say that your molecular Ke increased because temperature increased. Your molecular Pe also increased because molecule separation also increased. If you recall some of the relations that you saw in the previous page, internal energy is equals to Ke plus Pe. And also kinetic energy is proportional to temperature. Okay. So here when you look at your graph, you're going from here to here, your temperature is actually increasing with time. So because Ke is proportional to temperature in the first place, temperature increase, Ke increase, no? That's why here we say Ke increase. And then when you go and heat up your solid will expand a little. So your separation between your molecules also increases, but only slightly. So we will also say that your molecular potential energy increases. That's why here your internal energy is increasing. Okay. Now, once you have reached your melting point, which is over here, whatever heat that you supply won't cause any further increase in your temperature. You see there's a horizontal line here. Your temperature didn't continue to increase. It will remain this way until you melt off all the solid. All right. Now, one thing to note from here is this. At this stage here, your molecular Ke does not increase because your temperature remains constant. Just now I mentioned to you that Ke is proportional to temperature, your molecular Ke. If your temperature is constant, your Ke is obviously going to be constant, like your current case here. All right. So your heat supply causes a phase change from solid to liquid, which is known as latent heat. This latent heat is increasing your molecular Pe by increasing the separation of the molecules. At the same time, it's also enabling your molecules to overcome the forces that hold them together in a regular crystalline lattice. In other words, your bonds are being broken. Okay. Now, just now you see, I mentioned to you that when bonds are being broken, molecular potential energy increases, right? You can actually deduce it from the melting section. Okay, because you see, if I apply, look at this one now, IE is Ke plus Pe, but I already established that Ke is no change. Okay, I know that IE is increasing because I keep on supplying heat. So this would mean that Pe must also increase. So my Pe now is increasing because of two things. Number one, because my separation is increasing. And then number two, because my bonds are being broken. Okay, that's the reason why we say that when bonds are being broken, your Pe is increasing. It's because it's inferred from this section here. Okay, when you're melting a solid, you reach melting point. At this point, temperature is constant, Ke did not change. All right, but because you're still continuously supplying heat, you're increasing the internal energy, which means you're increasing the potential energy. So your potential energy here, if you try to relate what's happening here when the object is melting, separation of molecule increase, bonds are being broken. So it's from here that you can actually infer that bonds broken causes Pe increase. Okay, so that's what you're supposed to see from here. All right, and then after that you go on to section 3. Section 3 is where your solid has completely melted and then it becomes liquid And then when you keep on heating your liquid right now, you'll notice that your temperature will keep rising. So your solid becomes liquid completely and the temperature rises towards boiling point. At this point, your heat energy supply causes your internal energy to increase. It in turn causes your molecular Ke and your potential energy to increase. In your case here, because there's temperature increase, you have molecular kinetic energy increase. And at the same time, because you're causing the solid to expand, you have separation increase, so potential energy increase. Okay. Now, when you go to section 5, section 4 and section 5, it's actually a repetition of what you're seeing in the previous sections. Okay. So this one, you can just read it later on at your free time. Okay. But just learn to identify what is actually changing at the different stages. Is it PE or is it KE? Okay, because later on your stay and explain questions will require you to know this. Okay, last thing to do before we go on to your past years. This one is new to you guys. Now, under this chapter, there's something called first law of thermodynamics that you will learn. Okay, there's a second law, but the second law is not something you will learn. It's only in university. Okay, so for first law of thermodynamics, what you just need to know is this. Any increase in internal energy of a system is equal to the heat absorbed by the system and work done by the system and work done on the system. Okay, increase in internal energy is equal to the heat absorbed plus work done on the system. Now, written in equation form, it looks like this. Okay, if you write it in equation form like this, sometimes you might read it as change in internal energy is equals to change in heat supply, if you are given an equation that looks like this, by right, you would tend to read it as change in internal energy is equals to the change in heat energy plus change in work done, right? So in your current case, when you write it this way, it doesn't mean change in internal energy equals to change in heat plus change in work done. It actually specifically means this. Okay, increase in internal energy equals to heat supplied to system plus work done on system. Now it's because they assign a positive and negative to the variables and there's a specific meaning attached to them. If you're talking about the heat, delta Q, heat is positive if it is absorbed by your system, but it is negative, it is released by your system. Okay. When you look at work done, delta W, we will say that it is positive if work done is on the system, which causes a decrease in volume. It is negative if work is done by the system, there's an increase in volume. Okay, now work done on and by is almost always accompanied by these changes in the volume. Okay, I can give you an example. If let's just say you have a balloon now, okay, let's just say I give you a balloon, right? Now, this balloon is filled with air right now. Okay, so if you compress it, that means you need to apply a force. You need to apply force. This one will say work is done on system. Okay, if you have a balloon that's already filled with air and then somehow you want to compress it, when you want to compress it, it means you have to purposely apply a force to compress it. So in your case here, you're actually doing work on the system. So your balloon now looks like this right now. Okay, so it now looks smaller. So you have volume decrease. Okay, but let's just say that your balloon containing the air is at very high pressure. What will happen is something like this. Your balloon will now start to expand. Okay, so this one, force is applied No, maybe I better word my, sorry, I better just word my terms correctly. This one I can just say external force is applied. Okay, for the first example, if I want to compress the balloon, I need to apply external force. Work is now done on the system, which in turn causes volume decrease. But now let's just say I don't apply a force. I said that the air inside the balloon right now is very high. Sorry, the air inside the balloon is in a very high pressure. If I just leave the balloon there, the balloon will actually just expand by itself. So in my case here, I can say that force is applied by air inside balloon. Okay, so this one is what we will say work is done by system. Okay, there's a difference when we say work is done on system, work is done by system. So for the case where work is done on system, you actually need to purposely apply an external force. Okay, this one is actually from outside system. Okay, that's why we call it external force. So this external force is doing work on the system. It will cause your balloon to have a volume decrease. Okay, but on the other hand, if let's just say you don't apply any external force, you say that the air pressure inside the balloon is very high, the balloon will actually expand by itself from here going to something like this. All right, when it does so, we will say that the force is actually being applied by your air inside the balloon. Work is actually done by the system. Why we say it's done by the system is because that force actually did not come from outside the system. It's actually from inside the system. That's why we tend to associate it with work being done by the system. It's actually the system itself that is doing the work here. All right. So here, when work is being done by the system, it causes the balloon to increase in volume. Okay, so volume increase. Okay. Now, to know whether something is work done on system or work done by system, we tend to see the volume change. Okay, this is the easiest way to look at it. If you see a decrease in volume, it is work done on. If you see an increase in volume, it is work done by. Okay, to see whether your work is done on or by, just look at the change in volume, how it changes, whether it's an increase or decrease. And then from there, you'll be able to work out whether the work is supposed to be positive or negative. If work is done on, it's positive. If work is done by, it's negative. Okay, so this one hopefully is clear. So maybe I better just jump a little to something relevant since we're on work done. So if let's just say when you're talking about work done and you want to calculate out the value of work done, you will use this equation. For work done, delta W by gas under constant pressure, when its volume changes by delta V, the work done is actually given by this equation. You actually seen this equation before in your AS physics under the work energy power chapter. Remember this one? Work done was equals to pressure times change in volume. You know, it's equals to pressure times change in volume. This one was what you learned in AS physics. But this one was for gas at constant pressure only. Okay, you must have constant pressure. Only then can you find out the work done by gas. You're actually using back the same equation here. Okay, for work done by gas under constant pressure when its volume changes by delta V, your work done is actually pressure times change in volume. Okay, now if you have no volume change, you have no work done. Okay, so this one is how to calculate the work done. Okay, right? So this one ties back to what you have here. The one that you seeing here is to see whether your work is positive, negative. The one that you're seeing here is to calculate out the value of the work done. Okay, right, so that one should be fine. Okay, now then after that, you look at the last part. When you're talking about internal energy, delta U, it will be positive if system gains internal energy. It will be negative if the system loses internal energy. Okay, so this is how your heat, work, and internal energy is defined according to first law of thermodynamics. All right, they positive and negative have a specific meaning to them. All right, so now back to the original equation that you see here. Now it was mentioned that your equation for thermodynamic first law is delta U equals to delta Q plus delta W. Now remember in maths, if something is positive, you generally don't need to purposely write the positive before the variable, right? I mean, if let's say I tell you, maybe let's just say A is equals to B plus C. I did not purposely need to write positive A equals to positive B plus positive C, right? If I don't write anything, it's already assumed that these are all positive, isn't it? So it's the same thing here, all right? Even though it's, when it's written as delta U equals to delta Q plus delta W, because there's no other sign attached before the variables, these are all already assumed to be positive. So you try to relate it to what the positive negative means for all these variables. If it was positive delta U, it means gain in internal energy. If it's positive delta Q, it means heat absorbed by system. If it's positive delta W, it means work is done on the system. That's why here, when you read this, in thermodynamic first law, it means increase in internal energy is equal to heat absorbed by system and work done on system. Okay, so just remember this. All right, this one is really all in positive terms. So when you translate it into word, it means this statement that you're seeing here. Okay, so hopefully this is clearer. Okay, so with this, we're done enough to be able to do quite a fair bit of the questions already. So let's have a look at the questions. Thermal property, thermal first law. Okay, so you look at your temperature and thermal properties worksheet, the one that I just sent to you earlier today. If you look at temperature and thermal properties, you look at, say, page 12. Have a look at page 12. Okay, page 12. Maybe it's better if I just wait. This one. Okay, this one I cannot do anything because, yeah, this one I need to calculate some stuff first. Okay, just have a look at page 12, number 16P41. Okay, there's something here that relates to ideal gas, but I think it's a very simple one from there, so I think we can just do the question. Okay, right, so just look at page 12 or your temperature and thermal properties worksheet. This one we're talking about question 2. Now you have an ideal gas that is initially at a pressure of 1 times 10 power 5 and a volume of 4 times 10 power 4 meter cube at a temperature of 300 Kelvin as illustrated in the figure below. A change in energy of the gas of 240 joules results in an increase in pressure to a final value of 5 times 10 power 5 Pascal at constant volume. The thermodynamic temperature becomes T. Now for your current question, find out your temperature T. Okay, your gas actually went through two different, it went through from this initial state to this final state here. Okay, so they heat it up. Sorry, they didn't say they heat it up though, but they did. Yeah, but they didn't specifically say they heat it up, but it's already implied that it's being heated because you see there's an increase in pressure. Okay, so here they ask you to find out what happens when they go and increase, sorry, what happens when they heat up the gas to its final state. What is the final temperature T? Now this one you can actually use what you learn in ideal gas in chemistry. If you're taking chemistry now, or if you took chemistry before this in IGCSE or SPM, this one should be quite familiar to you. PV is equals to nRT. This is your ideal gas equation. All right. So you're heating up your gas from the initial state to your final state. Okay. You want to find out what is your final temperature here. Now you can use PV equals to nRT, and then you can use ratio to solve this. Now from state 1 to state 2, what were actually constant in your current case? Your volume is actually constant. They already told you in the first place it's constant volume. Your number of moles is also constant because your system is closed. Your R is your molar gas constant, is also a constant in itself. So Vn and R are constant, that means P is proportional to T. So this would tell you that T2 to T1 is P2 to P1. So that T2 is P2 to P1 times T. So you take the ratio of the pressures, multiply with your initial temperature. You're going to get a final answer as 1500 Kelvin. Okay. Right. So this one is 1. And then after, the last thing they want you to do is to find out the amount of gas. So the amount of gas here refers to the number of moles. You can actually check from the final answer from the units given. So you can again use back PV equals to nRT. You can use PV equals to nRT for state 1. You can use PV equals to nRT for state 2. It doesn't matter which one you use, right? Because you have the full information for both already. So here, if you're trying to use PV equals to nRT for state 1, pressure is 1 times 10 power 5. Volume is 4 times 10 power minus 4. The number of moles is what you want to find. Molar gas constant is 8.31. And then your temperature is the thermodynamic temperature of 300 Kelvin. So eventually your N is 0.016. Okay. You can also apply this for state 2. PV equals to nRT. When you sub in all the relevant values, you will still get back the same answer. Okay. So this is ideal gas. It's related to ideal gas. Okay, I haven't taught you ideal gas, but with the current knowledge that you have, you should have a bit of an idea of what this equation is. All right. Okay, now the next page is what is more relevant to what we've just learned. Now they tell you that the increase in internal energy of a system can be represented by this expression where delta U is Q plus W. Now state what is meant by the symbol plus Q and plus W. So from what you can see here, in the notes, I mentioned to you, if you have positive Q, it is heat supplied to system. Okay, heat is positive if heat is supplied or absorbed by system. Okay, so I think you can actually just say this also. If it's absorbed, it's actually supplied to system. Okay, it means the same thing. Heat supplied to system or heat absorbed to system. So positive Q is heat energy supplied to system or heat energy absorbed by system. Then what about positive W? Okay, so positive W is work done on system according to what we've written here. Work is positive if it's done on the system. Okay. So this one is like that. Now, then after that, they ask you for the gas that you've just seen in A, find out the value of delta U plus Q and plus W. Okay. What are the relative magnitudes there? Okay, so from here, you can actually do something like this. Now they tell you your change in internal energy. Here, the change in internal energy is 240 joules. How do I know that? Remember this thing here, this statement in the question? They told you this thing. They told you a change in energy of the gas of 240 joules results in an increase in pressure to some value to a constant temperature. So this one, a change in energy of the gas at 240 joules, this one refers to the change in internal energy. Okay. And because we have increase in pressure, this implies heating. Therefore, internal energy increase. Okay. So that's why I can say here my delta U is plus 240 joules. Not negative, but plus. Okay. Okay. Yeah, I actually don't need to put a positive now. If you don't put anything, it's already implied to be positive in the first place. Okay. So the one is the internal energy change. It's going to be 240 joules. Because in the question, we already found out that change in energy is 240 joules. This is change in internal energy itself. But how do I know it's positive or negative? It's because I saw that there's an increase in pressure. There's heating here. Therefore, you have internal energy increase. Actually, you can also deduce it from here. Because you see, your temperature is 300K. Your T is 1500K. You can also deduce it from here. Okay. I saw increase in pressure at constant volume, obviously temperature will increase. But I can also double confirm it by looking at the temperatures. 300 Kelvin to 1500 Kelvin, this is obviously heating. Okay. So heating, internal energy increase. Okay, so from there, you can also start to work out some of the other stuff. What is your positive Q? This one you need to relate back to your first law of thermodynamics equation. Delta U is delta Q plus delta W. Yeah, I think I don't use this color. I use this one. Okay. Delta U is delta Q plus delta W. Okay. So this one I already know is plus 240. So I need to find out this other two. Now, it will be easier to start off with the delta W. How do I know it's 0 in the first place? It's because you had constant volume. Therefore, delta W is 0. Your question already mentioned to you when you were heating it up, you had an increase in pressure to some final value at constant volume. Constant volume, right? So at the initial state is 4 times 10 power minus 4. At the final state is also 4 times 10 power minus 4. You have constant volume, so your work done is actually 0. Just now I mentioned to you, if you don't see any volume change, there is no work done. You have work done only when you have volume change. So over here, you don't see any work done because there's no volume change. Okay. So this one automatically tells you that this will be 0. So you see this equation now, the equation must obviously balance on both sides, right? So if this one is 0, this one is 240, this one must be 240, also positive. No? That's why my delta Q, sorry, that's why my positive Q here is 240. Okay. Yeah, to make use of this thermodynamic first law to deduce. Okay. Right. So this is somewhat the simplest example for thermodynamic first law. We go on to the next one. This one will be page 24. Okay, let's go to page 24. This one probably will be a better example. Okay, let's go on to page 23. Sorry, not 24. Okay, November 18, P41. This one, let's go through this. This one is question 2, I think. Yeah. All right, now, what is meant by internal energy of a system? What is meant by internal energy of a system? This is a definition that almost always will come out when it comes to thermal properties. So internal energy of a system is the sum of a random distribution of kinetic and potential energies of molecules in the system. Okay. There are 2 marks allocated. 1 mark is for you mentioning random. Another mark is for you mentioning the sum of kinetic and potential energy of molecules inside the system. Okay, so the word random there is a keyword that must always be there. If you just say it's the sum of if you just say it's the sum of kinetic energy and potential energies of molecules inside a system, you won't get the full mark. You only get half. You must say the sum of random distribution of kinetic and potential energies of molecules in the system. Only then you get your full mark. Okay, it's the definition for your notes. You can just copy it. Now let's look at part B. You have an ideal gas that undergoes a cycle of changes as shown in this figure here. Okay. Then after that, they tell you at point P, the gas has volume 950 centimeter cube, pressure 2.1 times 10 power 5 Pascal, and temperature 280 Kelvin. The gas is heated at constant volume and 97 joules of thermal energy is transferred to the gas. Its pressure and temperature change so that the gas is at point Q. The gas then undergoes a change from Q to R and then from R back to P as shown in the figures here. So here they are asking you, if you look at the next page, some of the energy changes that take place during the cycle PQRP as shown here with some missing blanks which you haven't filled in. You look at part 1 first. You're not required to fill in the blanks first. Just look at part 1. Part 1 is asking you, state the total change in internal energy of the gas during the complete cycle PQRP. Explain your answer. Okay. So for that whole cycle just now, where they gave you this little diagram, wait, let me just try and draw it out. You had this cycle here like this. Okay. You had this one, PQRP, 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 going from here to here to here. They're asking you right now for part 1, why is it that when your gas goes through the whole complete cycle like this one, why is it that my change in internal energy of the whole cycle is 0? Explain that. Okay, this one you have to relate to a keyword inside your question. Your question is saying that this gas is an ideal gas. You see, they already told you specifically that this one is an ideal gas. Okay, your keyword is ideal gas here. Okay, so let's look at what is the effect of ideal gas on internal energy. The first thing you learned just now was that internal energy is equals to KE plus PE. And now I told you that ideal gas has no intermolecular force, no IMF, therefore PE is 0. So it's from here that your internal energy is just going to be kinetic energy. This is for ideal gas. Okay, remember this one. And then after that, there's also another thing that I also mentioned to you. Kinetic energy is proportional to temperature. So this one would then imply internal energy is proportional to temperature. because internal energy is equals to KE, but now KE is proportional to temperature. This in turn means that internal energy is proportional to temperature. Okay. So this one is one thing you know. Now you look back at the cycle here. Is it correct to say that for one complete cycle, the temperature is unchanged? We know that it's 280 Kelvin here. That's correct. And after that, we have 372 Kelvin here. And then we had 332 Kelvin here. But when you went through one full cycle from P to Q to R back to P, you started off with 280 Kelvin, and then you went back to 280 Kelvin also for that one complete cycle. So your temperature is considered to be unchanged. At the same time, since internal energy is proportional to temperature, since T is unchanged, therefore IE is unchanged. No? I think this one I better put it as number 4, no? Just to see the flow there. For one complete cycle, the temperature is unchanged. So T is unchanged, therefore IE is unchanged now, since IE is proportional to temperature. Okay, so this is something like how you can see from here. All right. So how do you actually word it? The way you will word it is something like this. You will say that the final temperature is equal to the initial temperature for one complete cycle. There's actually no change in KE since internal energy of ideal. Oh, this one I explained it a different way. Okay, I explained it in a different way. Okay, so this one is one way of explaining it. If you look at the way I explained it, this one is based on a different way. Sorry, I think I probably overdid it. This one is based on this. IE is equal to KE. Okay, this one is explained based on this. Right, sorry. I explained it like that, but it doesn't seem that my question explained it. Wait, this one, let me just do this. This one is based on this. Okay, so this one, T unchanged, KE unchanged. Therefore, IE unchanged. Okay, right. So I explained it in a different way than what the answer is writing. So I'll just explain it like this now. Internal energy is KE plus PE. Ideal gas is no IMS, so PE is 0. So internal energy is just KE itself for ideal gas. But at the same time, I know that KE is proportional to temperature. So just now I mentioned to you, when you go through one whole full cycle, temperature is unchanged. So kinetic energy is unchanged. So since internal energy is just kinetic energy, IE is unchanged. No? This is what your current answer is saying. The final temperature is equal to the initial temperature. There is no change in your KE because kinetic energy is proportional to temperature. Since internal energy of an ideal gas consists of only KE, there will be no internal energy change. Okay, so that is what the question is trying to do for you here. Okay. This additional part here that I've just written is kind of like talking about the same thing now, all right? But because what I just explained, what I just wrote here doesn't seem to tally, I think I better just revert back to what I wrote so as not to cause any confusion. Okay. They will still tell you the same thing. It's just the way in which you want to word it. Okay. Right. So this is one part. All right, then let's complete the table. I'll just complete out the table and then after that we can call it a day. Right. On figure 2.2, complete the energy changes for the gas during the change from P to Q, Q to R, and then from R to P. Okay. So let's just complete that table. Now let's just look at it row by row. Sorry, column by column. I mean, column by column. For changes from P to Q, which was like this. Sorry. From changes from P to Q, which was like this, P, Q, and R, which was like this. Your thermal energy transfer to gas was 97 joules, okay? But what about the work done on the gas? You see, just now this one was pressure times volume. If you're going from P to Q, this one is constant volume. So therefore, work done is 0. So work done on gas is 0 here. Okay, that's why I know this one is 0. Now, what about the increase in internal energy of the gas? Now, you see this one has mentioned thermal energy, work done, and increase in internal energy. You would have to relate it to thermodynamic first law by default. So IE is, sorry, this one is delta U plus delta Q plus delta W. Okay, so in your case here, you already know that thermal energy transfer is positive 97. Work done is 0. So you look at the equation, you know both sides must balance. That would mean that delta U here must be positive 97. That's why your answer is like this. Okay. So this is for changes from P to Q. Okay. This is from P to Q. Okay. Now what about from Q to R? From Q to R here. They told you thermal energy transfer is 0. The work done on the gas is negative 42.5. So this one is pretty straightforward. You can just say that from Q to R, you will still use thermodynamic first law. Delta U is delta W plus delta Q. So in your current case, thermal energy supply is 0. Okay, now maybe I better just write it consistently for you. This one is delta Q plus delta W. Your delta Q is 0. Your delta W is negative 42.5. So again, same thing as before. If you try to balance both sides, this one will be negative 42.5. So your internal energy is negative 42.5. Okay, that's how you see this. Now, then after that, the last part, this is where you have to make use of what you just did here, where we tell you the change in internal energy of the whole cycle is 0. Now, they told you that work done on gas is plus 37, but they gave you 2 blanks. Okay, so this one, what is the thermal energy transfer? What is increase in internal energy of the gas? You can't work it out directly now. You have to make use of what you learned here. Just now, what you learned here was that the change in internal energy of the whole cycle is 0. Now, the change in internal energy of the whole cycle consists of 3 different stages. From P to Q, from Q to R, from R to P. So this one can be rewritten as this actually, where we tell you change in internal energy from P to Q plus change in internal energy from Q to R plus change in internal energy from R to P is equals to 0. Okay. Now from here, you already know the values of both of this, from which you can find this. Internal energy change from P to Q is plus 97. Okay, I don't need to put the plus sign. It's only going to make things confusing. This is 97 plus with negative 42.5 plus delta URP equals to 0. So a change in internal energy from R to P is going to be negative 52.5 joules. Okay, so I'm talking about from R to P. This one is from R to P. Okay, so this is negative 54.5. Now from here, you can then work out what's the remaining one. But this one you use delta U is delta Q plus delta W. Okay. So you already know the other two quantities where you say that delta U is negative 54.5. Delta Q is what you want to find. Delta W you already know is plus 37. So this one is what you want to find. You can easily see that delta Q is actually just going to be negative 54.5 minus 37, giving you negative 91.5 joules, which is this answer here. Okay, right? So there you have it.